So yes, good evening to all. So first of all, I will introduce myself. So I am Naren Vishwakarma, PhD scholar at under PMRF scheme at the Department of Electrical Engineering, Indian Institute of Technology, IIT Indore. So I will be taking the week 2 of this Principle of Communication Systems Part 2. So let's start. So my screen is visible. So this is the week 2 of the Principle of Communication Systems Part 2. So let's begin with the first problem. So I will read the first problem. So consider the digitally modulated signal with pulse shaping PT defined as some PT pulse is given, or pulse shaping filter PT equal to e raised to power minus 2a square TUT, where a is greater than 0 and ut is a unit step function, and the transmitted waveform is a naught pt, and the symbol a naught is to be transmitted at minus a by 2 and plus a by 2, and these symbols are occur with the equal probabilities. So first part is find the value of a such that the energy of the pulse is unity, and find the value of a such that the energy per bit that is EB is always a constant. So think over this problem and take 1 minute to solve this, then I will show the answers and give the solution. I think this problem is clear to all. Any doubt in the problem?
Is it BPSK constellation?
Yes, BPSK constellation.
Okay.
So you need to find the value of small a, this a, small a, and this capital A, this capital A.
Yeah. Here the intersymbol spacing means it is A, right?
Yes.
Yeah. Minus A by 2 to plus A by 2. The spacing is A.
Yes.
Right. Okay.
So you need to find the value of A in terms of EB, which is a constant, which is given. So you can write your answers in the chat box. You got some answers. So in the first question you have to find A such that energy of the pulse EP is a unity. This condition you have to fulfill. So for you I am writing the energy of the pulse. So energy of the pulse will be minus infinity to infinity P of t dt. Yes, you find the EP. Anyone? What is EP? So PT is given. Now I am solving this one. So PT is e raised to power minus 2a square t the whole square dt. Integration will be ut. So the integration limits will be 0 to infinity. And by solving this one, we get limits 0 to infinity, and by putting the limits,
The unit step function is multiplied, right? So that.
yes, unit A square, and it has been given that the energy has to be 1. So we equate this by 1 and we'll get A as plus and minus half. So it is given that A is greater than 0, we will choose A equal to half. So the first answer will be A equal to half. I hope you get this point. Now for B part, find the value of A such that the energy per bit is always a constant. So how do you to calculate the energy per bit? So there are only 2 bits, let's say, or 2 symbols or 2 bits. Correspond to bit 1, let's say correspond to bit 1, we are transmitting A naught is minus A by 2, and for bit 0 A naught will be A by 2, and I have already mentioned that the symbol occurs with equal probabilities. So the probability of occurrence of A naught would be half. So the probability of A naught or probability of minus A by 2 occurrence of is also half equal to probability of A by 2. So the energy per bit EB will be given by probability for the first let's say bit 1, and the energy of bit 1 will be A naught square, that is minus A by 2 the whole square into EP, energy of the pulse, plus for the second bit, that is bit 0, it would be plus A by 2 the whole square EP. So finally, so this is the average energy for 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 the occurrence of minus A by 2, and it is the average energy for plus A. Plus A by 2. So by solving this one, you will get finally A square by 4, and EP is already given as unity, so it would be A square by 4, and the value of A will be 4 EP under root, that is 2 root of EP. Clear? So in the second part, we will get A equal to 2 under root EB. So I hope this problem is clear to all. Any doubt in this one?
How did you calculate the average energy for bit 1, that is minus A by 2 whole square? I understand, but multiplied by energy average power EP, no? Why EP?
Because the transmitted, it has given the transmitted waveform is A naught PT.
Oh.
Transmitted waveform XT would be A naught PT, and the
Yes.
its value will be A naught
Yes.
square.
Yes.
So it would be A naught square PT square mod. If you calculate the energy, so it would be constant, then it would be minus infinity to infinity. It would be EP.
Okay.
Got it?
Yes. Thank you.
So problem number 2. So consider a random variable x which follows the Gaussian distribution with mean n and variance sigma square. The probability density function PDF of x is given by f of x, that is 1 by under root of 2 pi sigma square e raised to power x minus m square whole square by 2 by sigma square. Find its cumulative distribution function, that is CDF. And here we have given with PDF in terms of Gaussian Q function. We have already learned the Gaussian Q function in the video lectures. So the PDF is given, you have to find the CDF. So it is very simple. CDF, I have also given the hint. the CDF commutative distribution function is defined as f of x of u minus infinity to u f of x at x dx. But the condition is that you have to find in terms of Gaussian Q function. I hope you know the Gaussian Q function definition from the video lectures. It is clearly defined. And the notations also, capital X, it follows a normal distribution, that is this one, with mean m and variance sigma square. Just you have to put this integral here in this integral, this value, and keep substitutions or modify in terms of Gaussian Q function. So I will also write a Gaussian Q function for you. Have you understood the question? What is the question? Okay, so you have to do what is, you have to find the CDF in terms of Gaussian Q function. So f of x is, or the normal Q function standard, so that is minus infinity to u. F of x is 1 by root 2 pi sigma square to a minus x m whole square divided by 2 sigma square dx. Now a simple substitution. First of all, see the integral, this term. So a simple substitution we can made x by m by sigma we can substitute as t. So dx equal to dt by sigma, or sigma you can keep here. So f of x of u equals to yes, limits. So for lower limits, minus infinity, we'll put here minus infinity, so lower limit will be same, and upper limit in place of x we will put u, so u minus m by sigma 1 by 2 pi sigma square under root, and e raised to power x minus m by sigma the whole square, so it would be minus t square by 2, and in place of dx we will put sigma dt. Sigma is cancel out and it will look similar to somewhat in the Q function, that is 1 by 2 pi e raised to power minus t square by 2 dt. But one thing is there, limits are not same. See the limits are not same. Here the limits are from u to infinity, but here the limits are from minus infinity to u minus m by sigma. And for a normal or for a Gaussian distribution, this is a Gaussian distribution, and the Q function is from, let's say this is u, so u to infinity is defined, this is the Q u, okay, but this integral is from minus infinity to infinity, let's say, so minus infinity to u, let's say this is the limit u minus m by sigma, let's say this is some limit gamma. So what we have given, or what we obtained the integral in terms of this minus infinity to gamma, but what we have given with, we have to find in terms of Q function. So Q function is defined from this to infinity. So what we can do, like integrate from minus infinity to infinity and subtract this Q function. If we get this minus integral minus infinity to infinity whole integral, minus q of u, then we get this part, this portion. This portion will be minus infinity to infinity, the whole portion minus this portion. If we remove, then we'll got this. Okay. So what we can do? So the total area under any Gaussian distribution is 1. Total area is 1. So 1 minus, it would be u minus m by sigma infinity, would be 1 by 2 pi e to minus 2 square by 2 dt. And now this would be similar. Compare this one and you will get final result as 1 minus q u minus m by sigma. Clear? So the answer would be 1 minus q u minus m by sigma. Okay, I hope this problem will be clear to all. Or any doubts in this one? Yes, any doubts? Okay. Now the next problem number 3. So we have given the digital communication signal xt such that a0 pt with pulse pt defined as 1 minus 1, that is defined from 0 to 0.5 and minus 1 for 0.5 to 1 and 0 otherwise, and the symbol a0 is given as plus 1 and minus 1 and symbol duration is 1. Now signal is transmitted over additive wide Gaussian noise AWGN channel with autocorrelation of the noise nt is given as 1 by 4 del t, and the received signal is yt x plus nt passed through a filter with impulse response ht followed by sampling. Okay, we have also seen this type of questions in lectures also and assignment also. So what is the response ht that maximizes the SNR at the output of the sampler? So you have to find the response ht such that it maximizes the SNR at the output of the sampler, and this such type of filter is called as meshed filter. Correct. So we have to find the response ht of a meshed filter. The filter that optimal filter and that maximizes the SNR. So what is the answer in this case? So I will write the mesh
A option.
A option. Correct. A option. So the mesh filter output ht will be P of capital T minus T. This we have seen many times in the video lecture also. H of T, SR is given that the mesh filter output will be this the shifted and mirrored response. Okay. So ht would be P of capital T minus T, and the T is given as 1. So 1 minus T. Capital T is given. Capital T is 1. So first of all we will draw. So after drawing, if you first draw this one, so it will be very easy to solve. So let's say draw this pulse pt. So from 0 to 0.5 it is plus 1, that would be plus 1, and from 0.5 to 1 it would be minus 1. So 0.5 to 1 it would be minus 1. Clear? So this is nothing but your pulse pt. Now the first step, we can solve this question in 2 steps. First step, step number 1. So we will first convert our pulse pt to P of minus T. Okay, it's inverted response, so it would be just a mirror image, this one, that is plus 1, 0.5 minus 0, so it would be P of minus T. Clear? So it would be minus. Now in second step, so I am writing here, the second step would be delayed by T, sorry, delayed by capital T, that is T equal to 1. Okay, so nothing but P of 1 minus T. So we will shift or delayed this pulse to 1. Okay, so it would be shifted to 1. So as we can see that now the pulse, so it will be nothing but your h of t. So minus, so 0 to 0.5 it would be minus 1, and 0.5 to 1 it would be plus 1. So in this option, the A option, minus 1 from 0 to 0.5 and plus 1, 0.5 to 1. So A option will be correct. So this is the basic problem for the matched filter output. Clear? Is any doubt?
Can you just put back the PPT once again? Just want to check the answer. Yes. These recordings, are they available?
Yes, I am recording the session.
Okay.
And after the session, you can find the recording on the announcement page.
Okay, thank you.
Okay, can we move to the next problem, or should I wait?
Or is there is this the only way of drawing the shifted and inverted way? Is there any other way?
Yes, sir. By by drawing, drawing it would be easy. You can also solve mathematically by putting the variables and all that things, these variables, but it would not be very easy for understanding purpose.
Okay, so what you say is any simple such pulses, you do it graphically. That's what.
Graphically, yes. It would be easy.
Okay, thank you.
Now, fourth problem. So, consider the similar communication signal or the communication system where xt is a naught pt, same pulse pt, and but the symbols are different. So, please note that previously the symbols were plus 1 and minus 1. So, here the symbols are plus a to minus a, and the symbol duration is same, t equal to 1, and the signal is transmitted over the AWGN channel with autocorrelation. Rxx of tau is 1 by 4 del of tau. Now the received signal yt is xt plus nt passed through a filter with the impulse response ht followed by t equals to capital T. For the response ht that maximizes the SNR, again, what is the output noise power? So here we have to calculate the output noise power. For the same filter, for the same HT, you have to find the output noise power. I hope you know the formula for the noise power, or should I write so that you can solve?
Yeah, please write. Sir.
Okay. So the noise power for such system is already seen in the class also, the expected of n tilde. Okay. So it would be and not by 2 energy of the filter H, E of H, and not by 2 energy of filter is minus infinity to infinity H of dt. And further you can simplify by taking as P of t square dt. It would be same. So the energy here, it's to be noted, the energy of the filter H and pulse is same. This is the key result. It's the same, both are same. So finally you can write E by 2 E of H or E of P, both will be same. So I will give you by calculating E of P. You can verify after this class or something, you can verify that E of H and E of P will be same, that we have drawn in the previous problem. No? E of H we have drawn, so calculate E of H and I am calculating E of P.
So, autocorrelation of noise is 1/4 delta tau.
Yes, sir.
You have written R XX, right? You should written R NN
Oh, sorry.
notation here.
Yeah. RNN. Generalizing. Okay, RNN. Correct.
Actually, the otherwise the Fourier transform of autocorrelation is power, right? That
Yes.
also.
Yes.
Yeah. So if you take Fourier transform of RNN,
But you will get this is the input noise, NT is the input noise.
okay,
Actually, output noise will be N tilde.
okay, okay.
So if you take R of N tilde of tau, then you can take the Fourier transform, it would be same.
So tilde is a notation we use for output.
Yeah. In the class, sir has also mentioned in the video lectures.
Yeah.
Sir has mentioned the N tilde for the output.
Just sorry, I'm asking some dumb questions. That N0 is called what, energy per bit, or what is it?
No energy, not. It is the this one variance of the noise.
Variance of the noise. Oh, okay. Variance. But variance is also power. No, I'm getting confused. Variance also somewhere I read.
No,
It is.
directly variance is not the power. Directly variance you cannot say the power, because the variance, the power is defined as expectation of expectation of n square. Sorry. So variance is what? Variance is expectation. Let's for a general terms I am defining x square minus e of x the whole square. But the power is defined as the expectation of any random variable x of t the whole square. This is defined as power, but variance is different.
Okay. Okay. So the answer here is 1/2. Answer is B, right?
No, no.
Wait a minute.
There is not. I will
Output now.
solve this. I will solve now.
Yeah, EP has to be solved. Yeah. 1 minute.
So N naught, by comparing the Rn of tau by this one, for a general AWG and noise, we will comparing this, then we will got N naught as
And not as 1/2. Huh?
yes, N naught as 1/2, and EP will be, EP I am solving, EP is minus infinity to infinity p tau square dt, okay, minus infinity to infinity p of t square dt. So it would be, from this equation, it would be 0 to 0.5 1 square dt plus 0.5 to 1 minus 1 square dt. It would be p 0 to 0.5 minus t, sorry, plus, because 1 minus 1 square is 1, so 0.5 to 1, it would be 1 only. So EP is 1 and N naught is half. So N naught is half, again half is there, EP is 1, so you will get 1/4. So C option is correct. So I hope this problem is also clear to all, or any doubt in this one. So the basically you have to remember that noise power would be N naught by E of H, energy of the filter, and in this, for the matched filter case, especially for the matched filter case, the E of H is equal to E of P for matched filter only. No? Do not generalize this result. This is for the matched filter. Energy of H is equal to energy of P. So directly we will find the energy of P by this formula, and we will substitute in this one, noise power, and not by 2 EP, and this is a given, already given by comparing this form for AWGN noise. For AWGN noise, autocorrelation is given by N naught by 2 del of T. Clear? Now we will move to the problem number 5. So the same digital communication system, x of t equal to a naught pt, pt is same, and a naught, now a naught is different. A naught belongs to the BPSK constellation with intersymbol spacing d, okay, intersymbol spacing d is given. Now the symbols are not given, the distance between the symbols, or the constellation distance between the symbol is given, and the pulse duration t equal to 1. Now the signal is transmitted over the, again, the AWGN channel with autocorrelation of the noise is given as 1/4 del of tau. So the received signal is passed through a filter with the impulse response ht, followed by the sampling time small t equal to capital T. For the response ht that maximizes, again, the SNR at the output of the sampler, we have to find the resulting BER, bit error rate, or probability of error, bit error rate or probability of error. Probability of error from the video lectures, you remember, or should I write? Q of
Q of AEP upon square root of variance.
A square EP divided by N naught by 2.
Do we have to remember the formulas in the examination, sir?
Yes, for the general case, for the general case where the sir has derived the bit error rate for a digital communication system with some for this case, this is the generalized case where PT can changed, A naught can changed, but for this generalized case sir has derived the probability of error, this formula. No need to derive this again. This we have to remember. But if the system will change, if suppose the system is changed here, then we need to go with the derivation. So this formula, again I will write few things. So this formula is for the system x of t is a naught pt, where a naught belongs to the constellation like minus a to plus a, and the energy of pulse pt is E of p, which is the energy of pt, and autocorrelation of the AWGN noise is n naught by 2 del t. Clear? This formula is valid for these cases. So here Rx of tau is given as 1 by 4 del of t. So from here we can get n naught as in half, and symbol a naught belongs to the BPSC constellation with intersymbol spacing is small d. So for this minus a to plus a naught belongs to minus a to plus a, that is the two symbols. Let's say this is the two symbols minus a to plus a, that is the 0 in between, and let's say minus a is for bit 1 and plus a is for bit 0. So the distance between these two symbols is, what is the distance? This is called the constellation
2a.
Yes, that is 2a. In this case it is 2a, and what is given to us? That it is small d. So d is 2a, or we can say that a is d by 2 for the substitution. So we got few things, that is a we got, that is d by 2, and naught we got as half. Now what is remaining? E of p is remaining, that we also have done in the previous question. Energy of the pulse is, because the pulse is same, so the energy of the pulse is 1. EP is 1. Now substitute these values, this formula, and we got P of E as Q of A square is D square by 4, E of P is 1, and N naught by 2 is half. Cancel this 4, that is 4. It would be Q of T. So option A would be correct. Clear? This problem is clear? So this I have written from the video lecture. Sir has directly, sir has derived this one. I am using this result for this system. Now problem number 6. So consider a digital communication signal xt such that the pulse pt is 1 minus 2 mod t for minus half to plus half, where t belongs to minus half to plus half, and 0 otherwise, and the symbol a naught is from plus 2 to minus 2, and the symbol duration is 1. Now the signal is again transmitted over AWGN with autocorrelation of the noise is given as half del tau, and the received signal is passed through the impulse, a response ht followed by t equal to capital T. For the response ht that maximizes the SNR at the output of the sampler, what is the output noise power and BR at the receiver? So you have to find the output noise power here and BR. So few important things I will here. So PT you can also write as 1 minus 2t or plus t, sorry, writing 1 minus 2t. For positive t, so it would be minus half t to 0. Sorry. For negative it would be minus, so it would be 1 plus 2t for minus half to 0, and it would be 1 minus 2t for positive t, that is 0 to half. Clear? And 0 otherwise. Okay, you can also draw that signal, but I am not drawing it because I need an output noise power and BER, and A naught is given as belongs to plus 2 and minus 2. Compare it with the generalized, so the value of A would be 2. And the third important thing, the autocorrelation, that is n naught by 2 del t is half del t. So now n naught is 1. Now these are the given things. Now output noise power, in the previous problems we have seen that output noise power will be expectation of n tilde square, that is n naught by 2 energy of filter, or the, in this case where the, that is maximize the SNR, that is the match filter, so it would be energy of P. So you need to find energy of pulse, then you will get the power. And naught is 1, so you have to find EP. You need to find the energy of the pulse. Anyone got the answer for PT? Oh, sorry, EP? I am writing the integral and final write the values. So you solve this one, minus half to 1 plus 2t square dt plus, sorry, not 1, 0 to half 1 minus 2t square dt. So if you solve this, you will get EPS 1 by 3. Okay. So what we got now? We got energy of pulse EPS 1 by 3, n naught as 1 and A as 2. These three things we require for the output noise power calculation and BER. So output noise power PN would be, we have given n naught by 2, energy of pulse, that is 1 by 2 into 1 by 3, that is 1 by 6. And BR probability of error would be Q of under root A square EP by naught by 2. So here A is your 2, that is 4, EP is 1 by 3, and n naught is 1 half. It will be 8 by 3. Probability of error is Q of under root 8 by 3. So this is clear, or any clarification is needed at any step, CGC steps? So energy you have to find, previously we have seen, but the problem is different, so this requires some time. Solve in your free time then. Okay, so now the last problem of the day. So consider the digitally modulated signal. With pulse shaping pt equal to b by 2 sinc square b of t by 2, where sinc is given as sine pi x by pi x, and the transmitted waveform is a naught pt, and the symbol belongs to bpsk constellation, again -1 to +1, sorry. The noise at the receiver is additive white Gaussian noise with autocorrelation as 2 of del tau, and at the receiver signal is passed to the optimal filter followed by the sampling at t. What is the resulting probability of the error? You know probability of error, u of under root a square ep n naught by 2. So what things are given? A naught, compare it with minus a plus a, so a would be 1, n naught by 2, autocorrelation compare with rn of tau, that is n naught by 2, so n naught is 4, remaining is e of p. Anyone, how to calculate e of p? Can you directly calculate from this equation?
No, we take Fourier transform then
No, directly you cannot calculate, so we need to take the Fourier transform. So why we have to take the Fourier transform?
because time domain energy is equal to frequency domain energy, so that will be because rect it will be converted to rect or triangular, so that will be easy calculation.
Yeah, correct only. So the energy of the pulse, or the energy of any signal x, let's say x, is given as minus infinity to infinity mod x t square dt, which is given as minus infinity to infinity x of f square df in the frequency domain. It is equal. Energy in the time domain is equal to the energy in the frequency domain by which theorem it is? Parseval's theorem. Parseval's theorem. You go through this theorem, but now so you need to find first the Fourier transform and integrate over that. Then you will get the energy of the pulse, and you substitute here, you will get the probability of. Because the function is very typical, sinc square b of t by tau, so directly you cannot you cannot integrate over t, so you need to convert to the frequency domain, because in frequency domain the function will be simple. You remember? Anyone remember the relation of the sinc?
The rectangular.
No.
Yes, it is.
Rectangular pulse is not.
No, sinc square.
Sinc square, so it will be the convolution in the frequency domain of the two rectangular pulses.
It's a convolution. It is a triangular pulse.
Yes,
it will be triangular.
Yes, correct. Triangular pulse. It will be a triangular pulse. Correct. So I will write for you. Let's say the triangular pulse is denoted by triangle t by tau. Let's say the Fourier transform of this is nothing but tau by 2 sinc square f tau by 2, and this angular T of tau meanwhile is written as, how it is written, 1 minus 2 mod T by tau for mod T less than tau by 2 and 0 otherwise. Clear? So this is the triangular pulse. Okay, so this is the triangular pulse, and the Fourier transform of this is tau by 2 sin square f tau by 2. Okay, but this is given in time domain. So what is the Fourier transform of sin square? Sin square, let's say this is t tau by 2, let's say plus tau by 2. What is the Fourier transform? Duality property. So here the properties of Fourier transform. So duality property says that, what is the duality property? So I am writing the duality property here in this case. In the duality property, if let's say signal is small x of t, the Fourier transform is capital X of f, then you are taking the capital X of t. Now the Fourier transform will be small x of minus f. So this is called the duality property. So here it is given in the time domain. The Fourier transform will be del of minus f by tau, minus, because the triangular pulse is, so this pulse is just like this one, minus tau by 2 plus tau by 2. Okay, so so it would be an even function. Whether you take you take the mirror, you will take, so this is x of t and this would be equal to x of minus t. So it is nothing but triangular of f by tau. Okay. And for our question, it is given that d by 2 sin square dt by 2, and the Fourier transform of this will be del of f by d. That is nothing but 1 minus 2 mod f by b and 0 otherwise for mod f less than. Now the problem will start. Now you can easily find the energy of the pulse, that is minus infinity to infinity E of f square df, that is from minus half to 0, 1 double square df plus half to 1 minus 2f by b double square df. Now we will solve this integral. Meanwhile, I am writing directly. I have already solved this integral and it is given by.
So, sir, just a minute. Integral minus 1 by 2 to 0, 1 minus, right? 1 minus 2, 4, 4.
Yes, it's correct.
0, 2. No, and the previous one, minus 1 by 2 to 0, is it minus 1 by 2 to 0, 1 minus, right?
Why? Minus half to 0 and 0 to half is correct.
No, the limits are okay, but inside the expression.
Inside the expression. So, why? Because in the previous problem also we have seen, here yes, minus half to t to 0, it would be
Okay.
plus 1 because for the negative 1. Here I have already.
Thank you.
Yes, but limits were not correct. So correct the limits from 0 to half. So it would be b by 3. So now we got all the things we required for probability of error. So we have got PT as E by 3, A as 1, and N naught as 4. N naught was 4, no? Yes, N naught was 4. Now directly we can substitute these values in this probability of error, that is Q of under root 2 square PT by N naught by 3. So A square is 1, PT is E by 3, N naught, so 4, by 2, so it would be plus. I hope this will be clear. The problems of today will be clear to all.
So I have one doubt, sir.
Yes, yes, ask me.
So for a previous problem, if
Problem number 6.
it's is
Yes, yes,
if a duration will be if change R2 R3, we have to proceed the same procedure, or there is any change over here? Capital T.
capital T.
If it is one, for a simple duration, they'll be given as one.
1.
Suppose if they given us two, or if there is given us some other values, if there is any change in this procedure, any
Yes, yes,
uh,
yes. The pulse will be changed. Procedure actually, this T is directly related with the time duration of this pulse. Here
okay,
the pulse duration is from minus half to half. So the
okay,
pulse duration is 1.
okay,
So there is no need to given this T equal to 1, directly you can calculate from the pulse.
yeah, yes,
If pulse is from minus 1 to, let's say, 1,
okay,
then T will be
yes,
2.
yeah, okay, sir. Clear, clear. Yeah.
Yes, any other doubt in the last problem? I hope last problem will be clear, because PT is not a very easy function to calculate directly from PT. We will convert this function. We have converted this function to the Fourier transform, because of Fourier, by taking the Fourier transform, it will be slightly easy to calculate the energy of the pulse. Okay, so we have calculated the energy and other things. We'll put in this expression and got probability of success. So one thing we have to remember in all the problems, that we need a few things like energy of the pulse. We required the autocorrelation values of the AWGN noise, and the constellation, this A value, constellation of the uh, digitally modulated signal for the GPSK, because today I have taken PPSK only. So in the subsequent tutorials we will take some other ASK or other PPSK topics. Clear? So thank you everyone. So yes, any doubt, or should I close the session? It's okay. It's okay. Thank you everyone. So you can leave now if you